Hello everyone, in this video we're going to look into stars in the universe, one level beyond Earth and also the solar system. So let's look into first the properties of the sun before we define what is called a star. So the sun is made up of 75% hydrogen, 24% helium and 1% of other elements. And then we know that in the suns there's a process called nuclear fusion going on, and they radiate energy in the form of 40% visible light, like that we are seeing now, 50% infrared radiation, and 10% ultraviolet, which is absorbed by the Earth ozone layer. And let's define what a star is and whether the sun is a star. So the stars are celestial objects that emit their own light and appear to shimmer. So by looking at first glance, we already know that the Earth is not considered a star because it doesn't create its own light, it doesn't shimmer. But on the other hand, the sun fits the definition of what a star is. And the sun is also called a stable star, which is a star that is balanced by inverse gravitational force and outward radiation pressure. We're going to look into that later. But then just a recap here, this is the process that happens in the sun, nuclear fusion. And that's when hydrogen is transformed into helium and so on and so forth. And because the sun has such a high temperature, all matter only exists in the form of positively charged ions and negatively charged ions, electrons. And the energy is distributed over a large area. We know that the sun is much bigger than the Earth. Therefore, the temperature at the surface is a lot less than the core because it's being released, the energy is being released. And the other term to describe the sun is called the solar mass. So this is the mass of the sun, 2 times 10 to the power 30. And this mass is called the solar mass, just to make the scientist's life easy. Great, let's look into some of the more terms before we look into how a star is born. In the last chapter, we talked about light year. So, but how much further, like what is the distance of 1 light year? And the way we calculate that is that we first list down what is the speed of light, all right? Travel meter, 3 times 10 to the power meter per second. And then we calculate how many seconds are there in 1 year. So this is the amount of second in 1 year. And if you want to calculate how far 1 light year is, simply use 3 times 10 to the power of 8 in 1 second, multiply by this number, and you should get this gigantic number here, which is the one equivalent to 1 light year. So this will make our life easier in the next part of the video, because instead of saying this is the distance, we can just say 1 light year, the distance that light travel in a year. So let's move on and let's try to solve some distance question. The distance between the sun and the earth is around 8 light minute, 20 light second. It means 8 minute, 20 second to reach the earth. Given that the speed of light is this, how far away it is. So we can use the formula actually. Speed equal to distance over time. We got the speed, we got the time. So we only want to find the distance. So we're going to use speed multiplied by time. We have 3 times 10 to the power of 8 multiplied by t, which is in seconds, 500 seconds, because that's how many seconds in 8 minutes and 20 seconds. And if you put that into calculator, you should get this answer here, which is the distance between the Earth and also the Sun. Do note that there's one more term. The distance between the Earth and the Sun is called the astronomical unit. The astronomical unit. All right, so the second question, if a car travels at a speed of 60 kilometers per hour, which is pretty slow, how long would it take to reach the sun in a year? So again, we have speed equal to distance over time. We already got the time. Want to calculate what is, we already got the speed and the distance. We want to calculate the time, which will be distance over s. So we put everything into formulas. Just use the distance that we calculated and then divide it by 60. Then you'll get, this is the amount of hours it needs for the time for the car to travel. That's how it works. So let's look into how a star is born. Not the movie, but how a star, like our sun, is born from scratch. So initially, stars are formed from cool and dense molecular clouds made of gas and dust, mostly hydrogens. And what happened here next is that the gravitational attraction between the molecules, in the clouds, causes cloud to collapse and form a transfer of energy. And this transfer of energy, first one, is from GPE into kinetic energy as molecules are being pulled together by gravity, as molecules started moving. And the kinetic energy is then transferred to thermal energy as the molecule collide. And the cloud then contracts into a spinning sphere of superhot gas known as the protostar. Think of it as the baby star. Like, it hasn't become a star yet. It's not a stable star yet, but it's called a protostar. The process is on process. And the protostar continued to grow by attracting more materials from the molecular clouds. They're attracted by gravitational force. And then it becomes stable when the inward gravitational force is balanced by the outward force generated by nuclear fusion. So we know that in the molecular cloud here, gravitational acceleration is acting on it. Like, they are trying to attract more and more elements. So it's getting bigger and bigger. But then when it's balanced by the outward force generated by the nuclear fusion, it will then become stable. And if we look at what are the pressure outwards, right? And how it works is that hot bodies like the protostar, they radiate hits. And when they radiate hits, it exerts something called a radiation pressure. So as the star gets hotter, it radiates more and more pressure. And at one point, the radiation pressure will be equal to the inward pull of gravity. And this is when the star remains stable in size. That means it no longer attracts more elements into the protostar because now the force is balanced. And this is when we call a star stable, like our sun. Our sun doesn't go bigger now because it has become a stable star. And that's how a star is born. From when they are mostly gas and dust, slowly they just collapse and form together. And at one point, the radiation pressure equal to the inward pull of gravity. That's the point where the star becomes stable. And that's the process of how a star is born. And let's look into its life cycle, meaning what will happen after millions and billions of years. So as the star continue to burn, like carry out nuclear fusion, it will run out of hydrogen fuel. That's when nuclear reactions slow down, and this decreases in the radiation pressure that we talk about. So radiation pressure decreases. And the contraction result in the conversion of gravitational potential energy to thermal energy, because now the star is getting smaller and smaller, which means it get hot, and that's the contraction in visual form. And eventually, the core becomes hot enough for helium fusion to know. And what we have learned so far is just nuclear fusion. Nuclear fusion, that's when hydrogen atoms come together to form helium. But then as the star gets a lot hotter, now even the helium that's produced by nuclear fusion can start to fuse. And helium fusion requires a higher temperature due to greater electrostatic repulsion. So that only happens when the hydrogen fuel is running out. And then the heating of the outer shell causes it to expand, meaning it now expand. Oh, I just activated my Siri. Okay, great. And larger star with a cooler surface. So that's when the contracted star, because of helium fusion, it now gets bigger. All right, it now gets bigger and bigger, and it forms the red giant. So after the red giant phase, a less massive star will expel its outer layer to form a planetary nebula. The remnant core of the star will become a hot, dense, and white dwarf. So that's the planetary nebula. The definition is that it's a bubble of gas surrounding a white dwarf star. So that's when after the red giant phase. And when the sun becomes a white dwarf, it will shrink to 1% of its current radius. So meaning one day, as the sun undergoing this phase, it could be smaller than the Earth. And that's when it becomes a white dwarf. As it continues to cool down because there's no more nuclear fusion reaction, it will become a black dwarf, something like that. So the whole process is first, the sun run out of fuel, it contracts and becomes smaller. And when it becomes smaller, it got more thermal energy. It becomes hotter and hotter, which allows helium fusion to happen. And that causes it to expand again into a red giant. And then because helium fuel will also run out. That's when red giant will slowly become planetary nebula, eventually white dwarf, and it's cool down further, it become a black dwarf. So that's the whole progress of the life cycle of a star. So, and what happened to a star that is exceeding 8 solar masses? So, meaning 8 times the mass of our sun. And the process is quite similar with just a slight change. First is that massive stars also start as protostar before becoming stable, the same process. So the hotter core of the more massive star, because they're bigger, they can have more fusion. They're hotter. So they can fuse heavier element up to iron. So, and then what next is that after running out of fuel, like what we discussed just now, the star will explode and become a supernova. And the explosion will cause will serve as the raw material as future star and solar system, and they can briefly outshine the entire galaxies. All right, we haven't talked about galaxy yet, but stay tuned. So the fate of the remaining core after supernova depends on its mass. So if the core is less than 3 solar mass, so meaning after that, it's less than 3 solar mass, it will turn to something called a neutron star, right? And then, but then if the massive core collapse further, like if the core is a lot bigger, then it will eventually turns into what we know as the black holes, meaning they will absorb just everything. And here they said that even the light cannot escape from the black hole. And that's the life cycle of a star from how it is born and to how it is how it dies. Great. So next up, we have solar system, galaxy, and the universe. So in fact, the universe is much greater than the solar system. So let's read. Gravity causes stars to group together into galaxies, and the Milky Way is the galaxy that we are in, and it has around 200 billion stars, including our sun. So the sun is just one of them. And then I have selected this image here. They are basically, the dimension is 100,000 light years wide and 22,000 light years long. Meaning light need 100,000 years to travel from one point all the way to the other. That's to just show how massive the Milky Way is. And the universe contains billions of galaxies. So meaning, so this is the Milky Way, but then there's an outer layer here that contains millions of galaxies, billions of galaxies like the Milky Way. So just imagine how big the universe is. And here I have a fun fact. The Canis Major dwarf galaxy is the closest neighbor to Milky Way, 25,000 light years from us, meaning light needs to travel 25,000 years to reach the dwarf galaxy. So I have a silly question here. The solar system has existed for 4.6 billion years. How many times has the solar system traveled around the Milky Way in that time? So we can use the number of years divided by how long it takes for our solar system to travel around the Milky Way. So we can see that it's only about 20.44 times, so it's not a lot. So let's look into the universe. So Eddie Hubble discovered that the universe is a lot bigger than the Milky Way in 1925. Along with 53 other galaxies and dwarf galaxies, we are part of the local group of galaxies called the Virgo supercluster. So I will attach a video in the description. I think this guy did a fabulous job in explaining how big our galaxy is, which cannot be covered in this video alone. But then good to know. So before this, now we know where we are in the Milky Way, and we also know that there's a bigger world outside of us. But how do scientists know how long the universe has existed? So in order to calculate that, like how old is the universe, you need to understand a few concepts and theories. So be patient. First topic is called spectroscopy, which is a field that studies light. And then, so what happened here in short is that this scientist, Joseph Fraunhofer, he discovered this thing called the absorption spectrum. So we know that light is consisted of many colors, the rainbow color, and in the dispersion of light, we know that it can be split up. So what happened is that Joseph discovered that this thing called the absorption spectrum, meaning some of the light can be absorbed by certain elements. And by investigating light that travels, let's say, from the sun, we can identify what are the elements that are inside the sun just by looking at what light has been absorbed. So think of it like the barcode that identifies a object in the shopping mall. This line identified what elements are there in a certain planet. So for instance, if helium exists in a planet, and then we take in light from the planet, and we'll see that some of the light here has already been absorbed. So what Joseph did is that he collected all this different light here, this absorption spectrum, like a barcode, and then assign it to a specific element. That's how scientists can use the light to discover what elements are inside a planet. So that's the first concept you need to know, the absorption spectrum. All right? So how it works is that each element has a unique set of line. Because the wavelength at which each absorption line occurs are unique for each element. Now, that's why I said astronomer can measure the position of the line to determine which elements are present in a target. So if there is a lot of the light being absorbed, it also shows that there is a lot of elements in that particular planet or star. So that's first concept, absorption spectrum. The second concept you need to know, I know that it can be confusing, but I'm teaching it in isolation so that we can put all of them together later. The second concept is redshift. So when a star or galaxy move away from us, we observe that there is an increase in wavelength of electromagnetic radiation, including visible light. So this is known as redshift. So this is the absorption spectrum that we see just now. But then what scientists discover is that when the planet is moving away from us, getting further and further away from us, the wavelength of the light will get shifted. Meaning, instead of this part of the line that's getting absorbed, if the planet is moving away from us, it will shift to the right. It doesn't mean that the light turns red here. It just shows that the wavelength, they're being stretched as they travel through the universe. And by understanding this redshifting effect, we will be able to identify how old is the universe. Please be patient. I'll be talking about it soon. And the third concept you need to know is called the Doppler effect. This will show you, this is related to the redshifting. So what happened, I'll just define it. The apparent change in the frequency of a wave caused by the relative movement between the source of the wave and also the observer. So imagine this guy standing here, and as the ambulance passes through it, right, he will listen to sound like "Eeeeeing." So that's the sound that we hear when a car passes through us, and that's because of the Doppler effect. So I'll read through this. As a vehicle passes you, the volume of the sound rises and falls. The pitch increases as the vehicle approach. So here, this part, the pitch increases, higher frequency, and decreases as it recedes, like here. When it decreases frequency, it has higher wavelength. The sound wave is compressed in front of the vehicle as it approaches. This is because when the crest of the sound leaves the car catches up with it before the next crest of the wave leaves the car. The car is stretched out between the vehicle as it moves away. And understanding the Doppler effect is important. I will again put in another video in the description. I think this guy did some animation that describe how the Doppler effect is like. I think it will give you a clearer picture. But the main thing about the Doppler effect is that it explains why the occurrence of redshifting, meaning here, increased. Why is it that the stretching of the wavelength is an indicator that the universe is expanding? And to show you an effect, you can think of this ambulance here as planets that are moving away. Planets that are moving away. And this is, for us, could be the Earth. All right. As the planet is moving away from us, the light here the wavelength of the light here that they emit will get stretched. The wavelength will get bigger and bigger. And that's how it relates to the redshifting effect. And this shows that the planets, or in other words, the universe, is getting further and further away from us, just like the ambulance to the person here. And we can prove that this by looking at how these light are being stretched, how their wavelength become longer, how the redshifting effect occurs. So if we were to combine the redshifting effect and also Doppler effect together, you will be able to know, show that, hey, we have a proof that the universe is expanding. So why the Doppler effect matters? It's a property of all wave. So what we investigate here is sound wave, but it also works for light wave, right? So light from galaxies that are moving away from us is redshifted. This turned out to be the first important clue that the universe is expanding, and suggests that the galaxy must have been closer together in the past, meaning it's getting bigger and bigger. And this led us to the theory that the universe has a beginning called the Big Bang theory. And the scientists show that the universe could be created at a single point 13.8 billion years ago. And in order to calculate in exact what is the figure, there's another scientist who uses the Doppler effect to show how old is the universe. Let's look into it. So what Hubble's done, Edwin Hubble, what he did is that he plotted the distance of a planet and the speed where they are moving away from us. Like they measure the speed using the redshifting effect as indicator. He plot all these planets point together, and he found a linear relationship. And this shows that the further away a planet or a galaxy is from us, the faster it is that they are moving away from us. So after he plotted this graph, he discovered this, Hubble's law. It shows that the further something is from us, the faster it is they are moving away from us. And by looking at the graph, Hubble developed a formula called V equal to HOD, which is actually the formula for a linear equation. V is the velocity, D is the distance, and HO is simply the gradient of the graph. Gradient of the graph. And then Hubble constant, the slope, and also the ratio at which speed and which galaxies are moving away from the Earth to their distance from the Earth. So the importance of it is that it helps us to identify the age of the universe. So in this question, to prove this, we need to recap this formula called speed equal to distance over time. So V here stands for speed, and distance stands for velocity. Distance, D stands for distance. So in order to find out the age of the universe, we can use T equal to S multiplied by D. How fast they are moving, so which is V here. And by looking at this, using these formulas, we know that, okay, S over D. Okay, how it works is that, okay, we have these formulas, and then V equal to HO multiplied by D. And what we can do, because, okay, let's look into speed over distance over time again. To find out time, you use distance divided by S. So in other words, I can rearrange these formulas to be distance over V equal to 1 over HO. All right. So by looking at this, it shows us that if you want to calculate the age of the universe, you can simply use 1 divided by HO. HO is the Hubble constant, which is the gradient of the graph. And using 1 over HO here, if you divide it by, and that's the Hubble constant calculated by Edwin Hubble, is that if you use 1 over HO, you will get the time of the universe, which is how long the universe has existed. And if you calculate 1 divided by 2.2 times 10 to the power of 18, you will get the age of the universe, which is what we have here calculated, 13.8 billions. So that's how the scientist shows how old is the universe. So let's look into the other topics. So that's about it for Hubble constant and to calculate the age of the universe. And next one is the discovery of cosmic microwave radiation. So I'll just read this. The universe originates from an origin extremely hot and dense state known as the Big Bang, which occurred roughly 13.8 years ago, as shown by the Hubble's law and the Hubble constant. The universe has been gradually expanding and cooling ever since its creation from the unimaginable heat of Big Bang. So in the universe, atoms could not form as they would instantly ionize due to high temperature. The presence of charged particles like proton and electron caused light to scatter constantly. So in other words, universe expansion has caused the redshift of the light, the wavelength of the light here. So what these two scientists again did is that as they are doing their research, they discovered the microwave radiation. If you remember electromagnetic spectrum, microwave radiation is a little bit behind the light. And what they found out is that because light that emitted, like when the universe was just 379,000 years old, has undergo redshifting effect that causes its wavelength to increase. And at today, all this visible light has become what we now have, the microwave radiation. So this microwave radiation is also known as the cosmic microwave background radiation, possess this amount of temperature. So that's about it for all the theories involved in this chapter. It's a new topic. So if you have any question, just let me know in the comment section. Perhaps I didn't do a good job explaining this, but let me know how I can help you further. But then um, if you look at the specimen paper, I'll just leave it here. I want to explain it. This is the only past year paper we have on this topic. So they will ask you describe and explain how a stable star is formed, which is what we discussed in the past video. And the marking scheme is over here. So hydrogen gas and stellar cloud pulled together by gravity first, and then temperature of hydrogen increases and it forms the protostar, and nuclear fusion also occurs, and outward force balance this inward force of gravity, which is something that we discuss when we talk about the life cycle of a star. And they also explain what can you deduce from the cosmic microwave background radiation. A topic here that we discuss here is that the redshifting effect shows that, hey, the universe actually happens way longer ago, and then there's a one point which the universe began, which is known as the Big Bang theory. So if we look at the answers, you can use any of the answers here. And that's about it for this chapter and also this series. I hope that you learned a lot from it. It is also my second series on this channel, so I might not have done a good job, but let me know how I can improve in the comment section. And thank you so much for watching. I hope you enjoyed this. I'll see you again.